So let's recall what the inequality is. What were we talking about? We have an estimator, theta, hat, is just some function of our observations. Our observations are IID with law f, PDF little f. It's really f sub x, but there's going to be a lot of technical meat here, so the less I can write, the better. So let's just call it little f. And this is an unbiased estimator. It's a random variable for a parameter theta. So little f is really little f of x theta, but I will always just write little f of x. Okay? So think variance or mean or whatever that's sitting inside little f, and so it makes sense to differentiate little f with respect to theta. Okay? So just for example, little f of x is e to the minus x minus mu squared over 2 sigma squared with a factor of 1 over root 2 pi sigma squared. Okay, so then I can differentiate, let's call it a partial derivative since it's really a function of a lot of things, this with respect to mu. If mu is my parameter, if mu is theta, for example, in this example, then, well, you can work out what this derivative is, but it's something a bit annoying. So it's this thing, it's the same thing, it's f times the chain rule term, and the chain rule term, if you really want to know, is negative 2 x minus mu to the 1 with this same constant 2 sigma squared, and chain rule one more time because there's a negative mu. Yes?
Does that say 2 pi sigma squared?
Inside the radical, which is root 2 pi times sigma pi. Okay? So it makes sense to differentiate, even though the function isn't explicitly written as a function of the parameter, it's a function of x, we can differentiate it with respect to the parameter, and we get, again, some function of x, which is implicitly a function of the parameter. Does that make sense? Okay. So what's the theorem? The Cramér-Rao theorem is that the variance of such a thing has a lower bound. You cannot do better. Oh, what does it mean to be unbiased? What does it mean to be unbiased? It's that, what does it mean to be unbiased? Expectation of this random variable is exactly the parameter on the nose, the parameter that we're trying to estimate. Okay, so the Cramér-Rao theorem is that assume, here's a big assumption, assume that if you integrate f of theta, f of x, dx, and you differentiate this with respect to theta, it's the same thing as differentiating under the radical. I'm going to explain under the integral. I'm going to explain in a minute how this condition fails. There's a very simple way that this condition fails. But we're going to assume that we can differentiate our function under the, we can bring the derivative, maybe I should tell you now. How could this possibly fail? Well, it could fail if f, so this fails, if, not if and only if, but here's a condition under which it fails, there are others. If, for example, f of x is equal to 1 over beta, or 0, if x is between 0 and beta. In other words, a uniform distribution. The Cramér-Rao does not apply to a uniform distribution. Why not? Why can't I just differentiate with respect to beta, my parameter?
Because it's in the bounds.
Because it's in the bounds. You actually get a chain rule, a product rule type, chain rule product rule type term when you try to differentiate something that has the integrand and the range of integration depends on the parameter. Okay? But for lots of the other, all of the ft Gaussian chi-squareds, their ranges are not parameter dependent. A Gaussian ranges over all real numbers. Chi-squared ranges over all positive numbers. The t's and the f's have their ranges. So those ranges do not depend on the parameter you're trying to estimate. So this condition is satisfied. Okay? But it's not satisfied, for example, in the simplest case of a uniform distribution. So this is the big assumption. And if we make this assumption, then there is an absolute lower bound. You cannot get a better variance. Remember, we were talking about this when we were talking about optimal choosing estimators that are better than others, efficiency of estimators. And you want to get the ratio, you want to get the variance as small as possible. And you would compare two of them by taking the ratio of one to the other. That's how we got to the F distribution. But there's an absolute theoretical lower bound, again, assuming you have this, assuming you can bring this derivative inside, of 1 over the information, n times the expected value of the derivative with respect to your parameter of log of the PDF squared. Now let's unpack all of this. Let's unpack it with some simple examples. Here's something. So before we get to this, let's warm up. What is the expected value of 1? 1. What is the expected value? It's the integral over the whole domain of 1 times f of x dx. No complaints there. Let's differentiate both sides with respect to theta. Apply d theta. Okay? When I differentiate 1 with respect to theta, I get 0. I'm allowed to bring the derivative inside. I'm using the key assumption. I bring the derivative inside, and I get d theta f of x dx. That's fine, but that doesn't look like anything that can be written as an expectation. If I want to write this as an expectation, I can do something silly. So I have my d theta of f, and I'll stick in an f of x, and I'll divide by f of x dx. Of course, I'm only integrating over the places where f of x isn't 0. Okay? Now d theta of f over f, we can recognize this ratio as something else. It's the log. It's the derivative of the log. Does everybody see that? If I differentiate the log of a function, that's 1 over the function, chain rule, times the derivative of what's inside. So d theta of log of the PDF has expected value 0. So this whole thing is the expected value of d theta log f. Does everybody see that? In the case of the Gaussian, can we see this directly? I mean, we proved it for every distribution, but somehow that's not enough evidence until we see a specific case. F is equal to Gaussian, e to the minus x minus mu squared over 2 sigma squared, 1 over square root 2 pi sigma squared. We could do the derivative, we could use theta equals sigma squared, but then we get something really nasty. Let's again use theta equals mu. What is log f? The log of f will be some constant as far as mu is concerned, right? There's like a, well, let's take the log of this. So the log of a product is the sum of the logs. The log of this is easy, negative x minus mu squared over 2 sigma squared, minus log of root 2 pi sigma squared. That's the log of f. Ernest.
Why is the thing equal to 0 at the top?
Why is that equal to 0?
Yeah.
because we had an equation that had a 1 on the other side. 1 is equal to this integral, and we differentiate with respect to theta.
Oh.
The derivative of 1 with respect to theta is 0. Okay? Let's see if this really is true in the explicit case of a Gaussian. Here's its PDF. Here's its log. Now I'm going to differentiate with respect to theta. In my case, take theta equals mu. Take theta equals mu. So d theta, in other words, d mu of log f. There's no mu here. There is mu here. What's the derivative? Well, it's negative, what do I get here? 2x minus mu with this constant 2 sigma squared times the chain rule, negative 1. So this is a function of x with mu and sigma as parameters. What is the expected value of this? Well, plus. I have some constants. So this is 1 over sigma squared times the expected value of x minus mu. Exactly. What's the expected value of a random variable minus its mean? 0. Does that make sense? So we verified in this one case that yes, this calculation makes sense, and we see what's going on. Okay? All right. That was one thing that I needed. I need one more thing. I need the Cauchy-Schwarz inequality. Aside, Cauchy-Schwarz inequality. This is a fundamental inequality. Let's go back to finite dimensional vector spaces. Have we had linear algebra? Everyone's had linear algebra? So if I have two vectors, VW, in a finite dimensional vector space, and let's say I have an inner product.
Are we relying for complex inner product, or?
Let's start with real. Let's keep everything real, although this generalizes.
Okay.
But let's keep a real vector space with a symmetric pairing. Okay, just an inner product. Think about Rn. Let's say the vector space is Rn, and if I have vector v1 up to vn, inner product w1 up to wn, all I mean by that is v1 times w1 plus v2 times w2, just the usual dot product, vn wn. Okay? So you have two vectors in space. Here's Rn. I have a vector v, I have another vector w. What is the inner product of v and w?
You normalize it, you get the cosine.
Exactly. It's v times w. It's the norms of v times the norm of w times the cosine of the angle in between.
Yeah, the law of cosine.
Do you guys remember this? Okay. So if I take absolute values,
Well, the only reason that's defined, though, is because this works. Otherwise, that would make no sense.
that would make no sense, but in fact, the entire principle of functional analysis is what you can do for finite dimensional vector spaces, you can do for spaces of functions.
Yeah, that's true.
So we're going to do that in a second.
Okay.
Okay? So what's cosine? What's the value of cosine between?
-1 and 1.
Okay, so what's the largest this can get? 1. Okay? Of course, what is the length? It's the inner product of v with itself, square rooted. Right? Where the norm of v is the inner product of v with itself, square rooted. Okay? This applies just as well to functions. So, if now instead of v being a finite dimensional vector space, v is like L2 square integrable functions on your favorite measure space, well, let's keep it really kind of down to earth. If I have two functions, f and g, are functions from the real numbers to the real numbers, and they're integrable. Let's say they have however much decay you want at infinity. Let's say they're PDFs. Okay, if they're PDFs of probability distribution. If I integrate f of x, let's say over R, f of x times g of x dx, that's the analog of multiplying the values and adding them all up. That's the inner product. So that's the inner product of two functions on this vector space. So if you want to think of V as like L2 intersect L1, if you know what these things mean, if not, never mind, just we're going to work with analogies. But we don't have to work with analogies. We're going to work completely explicitly on this. I'm just defining the inner product of two functions when this integral converges. Okay? And the Cauchy-Schwarz inequality, so Cauchy-Schwarz inequality, this is a theorem, is that the inner product of f and g, let's write it in the form with squares, is less than the inner product of f with itself times the inner product of g with itself. So remember, these were the inner product of v with itself square rooted and the inner product of w with itself square rooted. So if I square both sides, that just makes it a little bit, I don't have to put square roots here, although you could just as well. Let's unpack what this says, i.e., the integral of f of x g of x dx squared is at most the integral of f squared times the integral of g squared. And I can't help but put absolute values because you can do this with complex analytic functions, where this is a Hermitian inner product instead of a symmetric one. But never mind all that.
What's slash one? No.
Where does the bar go? The bar goes on the back.
Yeah, okay. No,
So it's a sesquilinear.
Because Artin is annoying. It doesn't matter.
Yes, there are people who make mistakes in the way they normalize things. I mean, it's not a mistake. It's a mistaken choice of normalization. Okay. Let's prove this theorem. Can I give you a proof? I think we have time. It's very easy to prove. All you do is the following. So proof. Let me show you the theorem one more time. Okay, this is what we're trying to prove. So what you do is you let H be, you pretend you're dealing with vector spaces. You think like it's a vector space, and you take G, and you subtract off the projection of F onto G. How would you project F onto G? You would take the inner product of G with F, divide by the norm of F, and multiply by F.
Norm squared.
Norm squared of F, exactly. So F has some norm. I divide by that squared. This is exactly what you would do with vectors if you wanted to. If you want to think vector spaces, we don't even have to go R3. Here's F, and here's G. This thing is this. This is H. I take G, I subtract off the inner product of F with G, divided by the normalization of F. Okay? So I make F a unit vector. What this does is it makes both of these things unit vectors because it's the norm squared. So one of the norms hits here, one of the norms hits here. Work this out. This is like simple linear algebra. I'm trying to rush a little bit because Cramér-Rao is what we actually want to get to. So if that's your vector H, what you know is that the inner product of H with itself, well, it's a square.
So it's semi-definite.
So it can't be negative. On the other hand, what is it? So we have to open up all of these squares, so it's the inner product of G minus G inner product F over F inner product F, which by the way are now constants. These are constants, times F, inner product with itself. G minus GFF times F. Okay? This is not hard. This is easy. G times G, so I'm using the linearity. G times G. There's an F times F term, so that's going to be a plus this constant is just a constant, but we get it twice, squared, times the inner product of f with itself. And it's symmetric, so we get minus 2 times the inner product of g with the other stuff. gf, ff, times f. I'm just expanding the square. I have this thing, inner product with itself. That's the first term squared, plus the last term squared. And f, inner product f, is the only thing that's not a constant. These two were constants. They came out. And then g, inner product, the other thing, we get that twice by symmetry of the inner product. And now we're basically done. Let's simplify what this is. I have g inner product g. Let me move this square inside. So I have here g squared, g inner product f squared, f inner product f squared, times f inner product f. So that's 1 f inner product f in the denominator. Does everybody see that? And then what do I have here? This is minus 2. These are constants, so that's a gf over ff times inner product of g with f. Well, that's the inner product of g with itself, with f squared, divided by 1 inner product of f with itself. So there's minus 2 of them plus 1 of them. I'm left with minus 1 of them. Minus g inner product f divided by squared divided by f inner product f. And that whole thing was bigger than 0. Yes?
Why are those constants?
Why are these constants? So f is a vector. Once I take the inner product of g with f, what does that mean? That means integrate f of x times g of x dx. That's now a real number. So this is just some real number times a function. So that real number pulls out of the integral. Does everybody see that?
You're assuming f is non-zero at some point, right?
We're assuming that the integral of f with itself is non-zero.
Yeah.
If the integral of f with itself is 0,
Then it would have to.
then it's the 0 function.
Yeah. Because we draw the whole vector. Yeah.
Okay? In L2. As an L2 function, it's the 0 function. It can have non-zero value as that measure 0 set, for those of you that have had Lebesgue integration. And we're done. Let's move this to the other side. This implies that the inner product of g with f squared over the inner product of f with f is a lower bound for the inner product of g with itself. And that's exactly what we were trying to prove. When I move the inner product of f with itself to the other side. Here's the inner product of g with f squared is at most the inner product of f with itself times the inner product of g with itself. And again, if this, I hope this proof was sufficiently easy. Maybe I just did it a little bit faster, and I'm also stretching your brain muscles because we're doing functional analysis for, it's not even function, it's just
linear algebra.
It's just linear algebra, but in infinite dimensional vector spaces, which maybe you're not accustomed to. Just think about the finite dimensional example, and it's by analogy the same exact thing. And in fact, the proof is the same proof as your finite dimensional case. Okay, are we happy with, are we believing at least that there's something called a Cauchy-Schwarz inequality, and this is what its statement is? Okay, so I need the Cauchy-Schwarz inequality. I also need this fact. And let me put these two facts there. So I'm going to use the fact that whenever you have PDF f, you take its log, you differentiate with respect to whatever parameter theta, the expected value of that is 0, and I need the Cauchy-Schwarz inequality. Those two things together will lead to a rather, well, hopefully quick and painless proof of Cramér-Rao. So, what does Cramér-Rao say? We want to know something about the variance of our estimator theta. by definition, that's the integral. So I have x1 through xn. I take theta hat minus its expected value. What's its expected value? So let me be a little bit more explicit. Theta hat is a function of x1 through xn, but not a function of theta. The estimator doesn't know about the thing that it's trying to estimate. It's only a function of the sample. Does that make sense, Sakina? What's the expected value? So the variance is something squared times, it's the expected value of the variance, right? What's the variance? It's the expected value of the thing that you want the variance of, this random variable, minus its expected value, quantity squared.
So it's just theta?
So it's just theta, exactly. It's an unbiased estimator. Theta hat is an unbiased estimator for theta, so the mean of theta hat is just theta. And now I want to take the expected value of theta hat minus theta quantity squared, which means I integrate over all of the things that go into making theta hat. The PDF of theta hat is a multidimensional PDF. These are all independent. They each have law little f of x1 up to little f of xn, dx1 to dxn. Ernst?
Why are we just assuming that it's an unbiased estimator?
Yes. The statement of the theorem is assume you have an unbiased estimator. Assume you have an unbiased estimator. And assume that, that this condition holds. Okay, that's the variance. Any questions? Yes?
We did the Cauchy-Schwarz theorem. You started off with inner product of f comma g is less than or equal to f comma g, or f comma f times g comma g. And then you ended with g comma f squared in the end.
You mean in the proof?
Yeah. So when you stated it the first time, like when you like before you wrote the proof, you wrote
Yeah.
the theorem itself.
Yes?
Yeah.
Of Cauchy-Schwarz?
You have it squared. Oh, it is squared there. I guess I wrote it wrong then. Okay, that's fine.
Yeah.
All right.
Maybe the finite dimensional version I wrote without squares.
Okay. Oh, yeah. That's what it was.
And that's because this thing has a square root in it. So if I square both sides, I don't have to take square roots on the other side. In fact, most people, when they write the Cauchy-Schwarz inequality, will write it with square roots here and not a square there.
Okay.
That's the most, and there's a more general, okay.
But what's more general?
There's, you can do this with P's and Q's, which satisfies some. It's called Holder. There's a Holder inequality. It's a special case of something called Holder inequalities, which you can do with LP norms and LQ norms. Okay, we're not. We can do a whole course in analysis. I'd be happy to. I think you guys would actually be happy to also, but that's not why we're here. Okay, this is the variance. This is just the definition of variance. I have done nothing. Nothing at all. All right, what I want to do is let's look at something else. What is the expectation? So that's what the variance will look like. What will the expectation of theta hat minus theta look like? Well, again, it's a multidimensional integral, except instead of squaring, I'm not going to square. I'm just going to take this and multiply by my f's, dx1 to dxn. Right? The variance is the expectation of this thing squared. The expected value is this thing not squared. That's the only difference from this line to this line. And what is that expected value? 0, because it's an unbiased estimate. Let's differentiate both sides of this equal sign with respect to theta. Apply dd theta. I'm going to bring these inequalities back when I need them. Let me save them here. We're almost there. Apply dd theta. What's the derivative of 0 with respect to theta? 0. Here is where I'm going to use the fact that dd theta moves inside the integrand. The range of integration does not depend on theta. This is where I'm crucially using.
So you're just using it a bunch of times?
I'm using it a bunch of times. The dd theta of an integral is the integral of dd theta. Okay? Which is not the case for all, I mean, with f's here. The point is, the bounds, the support of f does not depend on theta. Okay? So I use it a whole bunch of times. I bring that dd theta in, and I have a product of two kinds of things. So I get dd theta of theta hat minus theta times my f's. Let me just write dx with an arrow. Plus, I'm just using the product rule. Leave the theta hats alone and hit the dd theta on the product of the x's, the f's, f of x's. Is everybody happy with that? So I apply dd theta to this integral. I slide a dd theta inside here because the integrand, the range of integration doesn't depend on theta. That derivative hits this function and it hits this function, which I'm treating as one function for a second. When it hits the first function, it just goes here. When it hits the second function, it goes there, and it's the sum of those things that's the product rule. I lost you, Yasser.
Why are you adding them?
So I'm just using the fact that I'm just doing dfg is equal to dfg.
Oh, it's the product.
It's just the product rule, f dg. Okay, it's just the product rule. I'm differentiating this, leaving this alone, plus leaving this alone, differentiating this. So far, so good? Let's look at both of those separately. Let's look at the first one. What is dd theta of theta hat minus theta? What is theta hat? It's an estimator for theta. So it's a function of the x's, x1 through xn. It can't be a function of theta because you can't estimate theta if you know what theta, while insisting that you know what theta is. It must be independent of theta. This derivative is 0. And what's the derivative of theta with respect to theta? So this is 0 minus 1. Also known as negative 1. Okay? So this whole thing is negative 1. And what is the integral of f of x1 through f of xn? Is 1. It's a probability density.
And the other thing we have to bound.
The other thing we're going to bound, exactly. The other thing we're going to bound. We're almost there. So now I have 0 is equal to negative 1 times the integral of fx1 through f of xn dx1 through xn. That's the first term. Plus, and this whole thing is 1, plus the integral of theta hat minus theta. And now the derivative is going to hit each of these terms. You can't see the derivative. Now this derivative is going to hit fx1, leaving all the others alone. It's going to leave f1 alone. It's going to hit f2, and leave the rest, and so on. So this is dd theta f1 times f2 through f of x2 through f of xn, plus f1 of x f of x1 dd theta x2 times f of x3, and so on, all the way down to the first n minus 1 are left alone, and the last one gets differentiated. It's just the product rule n times, hitting each one by itself. I claim, so let's see what this is. I claim that what I'm doing is, in each case, let me pull out of this an f of x1 through f of xn. So if I pull out an f of x1 through f of xn, what am I left in the first instance? So these guys all got pulled out. There was no f of x1 to pull out, so I have to put them in the denominator. And what was left here was d theta f of x1. Yes, that's the right reaction. That's exactly the right reaction. Now I pull out x1 and x3 and the rest. They got pulled out. I pulled out an x2, but I didn't have an x2. So let me put it in the denominator. F of x2. And what did I have? I had the derivative of f of x2 with respect to theta. And so on up to the last one, f of xn over f of xn. These are also known as d log, yeah. So these things are d theta of log f of x1 plus d theta log f of xn. All right, we are almost there. We want to apply Cauchy. So this whole integral, this integral is equal to this whole big integral plus -1 is equal to 0. So it's equal to 1. Okay? So 1 is equal to this whole integral, theta hat minus theta, d theta of log f x1 through d theta log f of xn. And then I'm going to do something funny. I'm going to write the f's as f of x1 through xn raised to the 1/2 power, and f of x1 through xn raised to the 1/2 power. So I split this f, I split these f's as two things which I square root. Yes, it takes a minute to write.
Wait, so on the top, that was f of x1 minus f of xn, right?
No, that was dot, dot, dot.
Oh, okay, that's what.
Dot, dot, dot.
Yeah, I was confused.
So it's the product, f of x1 times f of x2 times f of xn. So here's the dot, 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 and here it is again. I put it twice, but if I take the square root of both. That's an equality. It's also an equality if I square both sides. And now I want to use Cauchy-Schwarz. What's my first function? This is my first function. This is my second function. Have a good break. So the integral squared of something times something else is at most the integral of this thing squared, theta hat minus theta squared, times this thing squared, but it's to the 1/2. So it's just f of x1 through f of xn dx1 through xn, times the same integrals, but now of this thing squared, and that's d theta log f of x1 plus d theta log f of xn squared times this thing squared to the 1/2, so it's just f of x1 through f of xn dx. And that is all bounded below by 1 squared. So here I'm using Cauchy-Schwarz. Now we're really almost there. We can simplify this. If we square this out, by the way, what's this?
Variance.
The variance. It's theta half minus theta squared times its PDF. This thing is literally the variance of theta. And that's good. We have a lower bound for the variance. Now what is this side? This side is the integral of this square. So what does a square look like? It looks like d theta log fx1 squared plus d theta log fxn squared plus the cross terms.
So sort of triangle inequality thing?
Not a triangle. I'm not doing I'm just squaring everything out.
Okay.
I'm just squaring everything out. I have a sum of things that look like d theta log of fxi times d theta log of xj with I not equal to j. So this is sum over I not equal to j of things like this times my density. Okay? Almost there. Now so now we'll break everything up into little pieces. So what's dd? What is this? Well, it's the expected value of dd theta of log squared. How many of them are there? N. So far we have this variance out front, and we have n times the expected value of dd theta log f squared. And now what happens to the rest of them? It's a sum over I and j of the expected value of dd theta log f of xi times dd theta log f of xj, close bracket. But xi and xj are independent. So it's the product of each of these expectations individually. So this is the expectation of dd theta log f times the expectation of dd theta log f. But what is
0.
dd theta? Thank you very much. dd theta log f has expectation 0. So these things are all 0. And the variance times the information is bounded below by 1. That's Cramér-Rao. It's just Cauchy-Schwarz and differentiation and differentiating under the integral sum. Okay? So if you really want to understand this, let me suggest 2 exercises. Exercise 1, verify in the case of the Gaussian. Let me write this down. Exercise 1.
Can you pull that page up a bit?
Yes, sorry. Exercise 1, verify for Gaussian, which satisfies the Cramér-Rao assumptions that mu hat is optimal, that our estimator, x bar, is an optimal estimator for mu. In other words, the variance is equal to 1 over the information. Can't do better. And exercise 2, compare the information in the case of log f squared for uniform on 0 to beta, the one for which Cramér-Rao fails, with our estimators n plus 1 over n yn, which we computed the variance of. We computed this variance, and that variance was way too good. That variance was really, really tiny compared to what Cramér-Rao says any variance could possibly be. It's better than the information. And that's because where the proof fails is that we can't differentiate under the integral set. Okay? If you do these two exercises for fun, you will have a better understanding of the Cramér-Rao inequality.